Hello everyone. Today is the second session of machine design, and we'll be learning about machine design and how it works and what are the top. We'll be discussing about the important topics of material selection in machine design and what are the techniques we use actually for material selection in a machine design or in designing process. Fine. So in material selection, we have to be very cautious, or you may say, which need to be very specific and very much sure, because it's a matter of safety. So for the material selection. So for material selection, the first most is the most important is the your safety. Important is safety. SAFTY, safety. You need to maintain safety. You have to go for higher standards of safety. You cannot compromise with this. Number second is the function. Number third is the cost. Now remember, this everything comes in hierarchy, but sometimes it happens that some if you compromise with the cost, the safety may not be as per your requirement, the functionality may not be as per your requirement. So it's you may say that this cost is interconnected with everyone, because everything relates to money. So the cost is interconnected with each one, so it's not directly connected but it's interconnected. But we have to be very serious on this note. Now for at first we need to understand what is safety and how does safety, for safety what are the procedure we follow. Now engineering materials have been categorized in two types. One we say ductile. Number two is a brittle. Now here comes why ductile and brittle, why not other materials? You may ask me. We have iron, we have we could talk about iron, metal, non-metal, that may be your polymer, that may be your uh, your ceramics, your everything. It could be anything, alloy. So you may think, because these are the most descriptive one, this goes for the types of material we have. These are sub branches. But since we are talking about material selection in machine design, and machine design, the first priority is the safety. Now the comes to the point. Now the point comes, what is the safety? What is safety of a design? Safety of a design is the fracture. Now it's not fully understood why fracture happens and where it can happen. We have mathematical models, the simulations, where we could actually say that it may the fracture or the failure may happen on this point of this bar, this point or this point. So it's an assumption, but it's not 100% foolproof. So we cannot assure that the failure or fracture could happen. So that's why we have seen the types of fracture. So with considering that types of fracture, we have segregated material in two types. One is ductile and another one is brittle. Number one. Now what happens in ductile, as we know, as per the definition, we know that ductile material can be drawn to wear. It could be drawn to wear. Yeah, drawn to wear. That means it could be drawn to wear. That means you may use this, you may bring where you can make wears, or it may be it is stretchable. So that's why we say that this material to have the fracture, or we observe the fractures, the fracture type is over here. It is cup cone. I hope you have studied in the early previous semesters in material science, where you know about the cup cone. That means the deformation area will be in the cup cone manner. That is, one will be one end will be like a cup, another end will be like a cone. Now the brittle comes with a added advantage that it could be made to sheet. Okay, these two properties, but the thing is that the formation of of the brittle material is sudden. That means it will break any moment, like chalk. It breaks in any moment. So what happens is we could consider brittle material as sudden. Now note one thing, this is for your understanding, this is for your knowing. Don't you don't have to, you have you if you remember, it's in the research lab, we talk this in the research, we do research for this one. Now every material have both qualities, and that's why I'm telling it's note. Remember, every material have both qualities, both properties, that you cannot say the mild steel is completely ductile or a chalk is completely brittle. There is the thing is that the graph, there is a graph of ductility and brittlity. It depends on the temperature, it depends on the transition temperature, how the as the temperature increases, the ductility may increase or decrease. That depends on the material types and the material features. So you need to remember the ductility and brittlity depends on the material temperature and the material compositions and everything. So a element cannot be 100% ideally ductile and ideally brittle. It's not possible, it is not possible. Fine. Next is, for understanding ductility we may draw two graphs. One is stress, that is denoted by sigma, and one is strain, that is denoted by epsilon. So the graph comes in this manner. Fine. So the points you need to remember, the point is here, number 1. Second point is assumed to be here, number 2. First point is yield upper yield point, or in some books it is also upper yield stress. Similarly, it's the lower yield point or lower yield stress. Here in this position the cup cone structure starts. Now let me let me brief you about this graph. This graph is valid for ductile materials. I mean ductile property of the material, that is not since I am telling that not we consider one material to be ideally ductile, but it's not 100% foolproof. Now next is here is the ultimate point, or where the stress is maximum. Fine. And this is the most dangerous or the vulnerable point, that is called your fracture. Fine. So we have 4 points, 4 basic points. Let me name 3 and 4. So we have basically 4 points. One is upper yield point, lower yield point, ultimate point, and fracture point. So from here we could consider the maximum stress is the maximum stress we can find over here. The maximum stress is over here, and this from this zone onwards, it's an entire elastic zone. That means beyond upper yield point, that means beyond, let me zoom it, beyond upper yield point is the plastic zone. That means if there is a deformation, it will be permanent. Okay. Fine. So this zone is termed as, let me this zone is termed as plastic. That means the deformation on this zone is non-retraceable. Okay. And this zone, this zone is nothing but your elastic zone. Elastic. That means if you load, if you apply a load or a force in a body in elastic zone, the deformation can be can be retrackable. That means it could be bring back to the original state. But whereas in plastic zone, it is not possible. Now, similarly to this one, here comes another graph for our brittle material. Brittle, brittle. Now the graph is something like this. Though it doesn't have any physical evidence of elastic yield point, or you may say that uh, ultimate stress. So what we do is that to find the yield point, we consider offset value. To make it very easy, we consider 2 to 3% of strain from here. Let me write it over here: 2 to 3% of strain. So in the 2 to 3% of strain, we draw a parallel line, or parallel line to this line, parallel line to this line, and we consider this point to be our yield point for brittle material. But it's all about theoretical and mathematical model. It doesn't have any physical significance, but but note, the physical significance is very less. So yield point in brittle material is not so considered. If I need if I need elastic deformation, if it is demanding, so I have to go for this ductile material. But in some cases, in few cases, we know that this yield point is maximum. So what we do, we could take the risk, or we could accumulate the risk, or we could, since we could overcome the risk, that's why sometimes in some cases we take the brittle material. Now this is all you may ask that why it is happening, and what are the other things which we encounter while material selection. The most after that, most important thing comes the cost. Why it is very important? Why it is very important? Now I have to discuss about it, because there is a rule. The rule is rule of third. Rule of third. Third. Let me briefly say brief about this rule. The rule says that if the applied load is 10 kilonewton, 10 kilonewton, the material should, if the applied load, applied load is 10 kilonewton, so the material should withstand 30 kilonewton. But material, but there is a catch. Now you may ask me, what is the catch? That's why I am giving the star. There is a catch. The 30 kilonewton, it should withstand 30 kilonewton. It is the first guidelines, first rule. The second guideline states that it should be in the elastic limit, and it should follow the rule of third. That means, if let us consider this to be our ductile material, so let me draw this graph. Since we know that it should be under elastic limit or elastic zone, what we do is that it should not exceed the loading should not come over here. It should not be come over. That means the loading should be under the 30% of yield point. That means if the yield point is 90, upper yield point is 90 Newton per millimeter square, kilonewton per millimeter square, then the 30% is 30 kilonewton per millimeter square. 30%. Let me tell you, this is 30%. 30%. So what happens is that this material will only be allowed for machine designing, but it comes with a very cost sometimes, not on every time. So sometimes we negotiate with cost. That's what I mean to say. While doing a design, we have to remember two laws. First law is rule of third, where you have to apply a 33 times more the low material should withstand, but it should be under elastic zone, and this elastic zone should be segregated in three parts. That means 1 2 3. Fine. And the loading should be just over here. It should not exceed here or here. It is not acceptable. That means the applied load should be beyond, be in this range only. Fine, this is what the main concept. Now you may ask that why it is done. It is done only for safety, but still maintaining this also we are getting lots of fractures and lots of many things. Next session we'll talk about the loadings and why it happens and what the load can occur, can do for your, can how it works for a beam or for a member. Till then, be safe. Thank you.